almost like a foundation for preparing your learning problem into your reinforcement learning. So this MDP is a key. Whatever problems you are working with, if you are saying I will be able to define MDP for my problem, then definitely you can apply reinforcement learning. So which is definitely not a major concern if you are working with a control problem. So any control problem definitely can be formulated as a MDP, which will be a foundation for your reinforcement learning. And there are different sub-algorithms where this MDP can be solved. I'll introduce you to this dynamic programming as well as this TD, temporal difference learning kind of approaches. Then I have some case studies where we got some results both on model-based and model-free control. Of course, those who already know reinforcement learning basics, this Q learning is a model-free or a real-time implementation of this reinforcement learning, which is the retrained version of this reinforcement learning. So I'll be showing you algorithms, and I'll be giving you the explanations on what all these equations represent and how we can utilize this for the, any control applications. Maybe whatever case studies I'm giving you, those things you can apply in your control problems. So the way we are forming the MDP, all these things definitely I will be explaining. Now, the introduction, since this FTP is focusing on machine learning, of course, all of you will now have an idea on machine learning. So this is basically we are trying to make our computer to learn something, right? It is not like direct programming of learning something. The popular examples you will come across this. If I'm having something like I have some data in A, some data in B, okay, I have to do this simple addition. Okay. So far, what we used to do is I'll create a computer program, okay, which will have a function, and that function will collect A, and that will collect B, and that will give me C. Right. So this is what our traditional approach. Okay. Traditionally, we used to program the computer to do that. So maybe it's a straightforward function. I'm able to do this. Imagine if it is a completely a nonlinear case or a complex function we are trying to do, right? Which I am unable to create a function. In that situation, what we are going to do is we are going. So in this particular case, A and B are inputs, and I'm having some target, right? So what we are going to do this, I'm going to ask my PC or my computer pro to get these inputs, okay, and also it is going to get these targets, and this is going to give me, this is the function you are trying to learn, right? Once I get this function, then I'll be able to implement this function back, right? So this is what the idea of machine learning is. So instead of hard coding something, making my system to do, I'm going to make my system to learn itself to do something, right? So in that situation only, we have all these kind of supervised learning, unsupervised learning, reinforcement learning, all these other subclasses, right? A clustering algorithm or a classification algorithm, regressions. So there are so many applications we are having. So if you are seeing the basic idea, this is the idea. Instead of hard coding my system, I'm making it to learn itself, right? Because once it learns itself, of course, the learning gives you a better result instead of making you strictly do something. Right? So that is the objective of machine learning. Okay? So any complex task, okay, maybe a function learning, any other complex task, we are able to make machine learning to apply on the system so that it will be able to learn and do. Okay? So that is the objective. So if you're seeing the broad classifications, right, we have this supervised learning, right, which is more task driven. So the example I gave you, there is a task. Okay, I'm trying to make the system to learn a function, right? Or I'm trying to make some classifications. So I already know this is what it is classified into. Okay, something like in your biomedical applications, I have to classify it into healthy, non-healthy, okay, or this particular disease. Okay, all these things, there is a task for you. Okay, So the supervised learning is more kind of a task-driven learning. Okay? So I know there is a task. Whereas unsupervised learning, this is more data-driven. Okay? So I have a database, and I have a bunch of data. I don't know exactly what task is going to be the end application, but imagine this clustering kind of application. So from the given data, I'm able to say, okay, I have a database. In this database, my algorithm is saying there is a cluster. Okay, all some 1,000 data form one particular cluster. They are behaving similarly. There are another 1,000 data. They are behaving similarly, right? So like that, I'm able to cluster something. Okay, so this is more data driven. So there is nothing like a task driven for unsupervised learning. Okay, so this is more data driven. I have this data, how it is behaving. Based on that, we are doing something, comes under unsupervised learning. Now, this reinforcement learning, what we are going to discuss today, it forms somewhere in between this. Right? Most of us used to say it's somewhere between the supervised and unsupervised. But of course, it's a separate class. Okay? This is more related to how we are learning. Okay? Maybe you can try, you can say how we are training our pets. Okay, your pet dog or your pet cat. So how you are making it to do something. Okay, those kind of learnings comes under reinforcement learning. So definitely reinforcement learning also inspired by human learning only. Okay, so we say neural network is from a human characteristics. So fuzzy is coming from some particular human behavior. Like that, this is also coming from some of the human behavior. Right. So the objective here is more like we are creating an algorithm, okay, to learn some policy. Okay. So this particular term we are going to use repeatedly today. Okay. It is trying to learn a policy. So from a control system point of view, if you are asking, so the algorithm is trying to learn some controller output. Okay, what output I should give. So what signal I should give as an input to the system so that it will give me a desired performance. Okay, so that policy it is going to learn. The algorithm is learning. Okay, so that policy will be based on what I should do given the situation. Okay? So for that particular situation, what I should do. Okay, that is what it is learning. Okay, of course, this is what supervised learning also you will say, right? So given the situation, what I should do. But the thing is, the learning style is changing. Okay, there are some similarities. Anyway, I'll describe those things also. Okay, but this is our objective here also. Right? So learn something to do given a situation. Okay, so now itself I will relate this with our control application. Given one particular set of state condition, state variables, what action I should take? That is our controller, right? So if I am telling you this is the kind of state variables present, okay, one set of state is present, accordingly you are trying to say this should be my controller output. It may be multiple or single output. So this is how we are going to relate this reinforcement learning with the control application. So there is a controller, it is going to learn given a situation what I should do on the system. So that is what it is going to learn. Right. Now, how this is going to happen here is every action we are taking, it is going to have some impact on the system. Right? If I take some controller, feed some signal from the controller to my system, definitely it is going to exhibit some properties. Right? If it is a robot, is going to move, or if it is a temperature control system, the temperature is going to rise or it is going to decrease. So like that, it is going to have some impact. Right? And based on that impact, we are going to collect rewards. Okay? So this is what we are going to get from the environment. Okay? So using these rewards, we are taking by taking some actions on the system, we are going to accumulate these things so that I will improve my policy. That is what the reinforcement learning is. So initially you are having a blank knowledge. Okay, so you are doing something, getting some rewards. It could be punishments, right? But slowly we are learning what to do given some situation. Okay, so this is what our controller is also going to do. Okay, in the learning phase, the controller is taking different things, doing different things on my system. Okay, it could be a model based or model free. It is trying different things. Slowly, it is learning something. Finally, it is able to produce a better control actions. So that is our objective in reinforcement learning. Okay. So this is what happens here. So now I'll quickly compare this supervised learning because there is a lot of confusion or there is more similarities. Okay, when you are starting, maybe once you start coding all these things, you will understand the major differences. But in the initial phase, many of us will have this problem of differentiating this supervised learning and this one. Right. So supervised learning is more like there is a supervisor close to me. Yeah. So when I'm in the learning phase, somebody is there to hold my hand and they are telling me, do this, don't do that. Okay. So this is correct. This is wrong. Like that, there is somebody holding my hand. Okay. I used to give this bicycle learning problem. Right. So maybe our father or uncle or someone, there is a person holding holding us, saying different actions to do. Okay, pedaling or they ask you to sit straight and look forward. Okay, hold your your hands properly. All these things they keep telling you. Okay, and you are listening to them and you are doing something. So this is exactly supervised learning. Okay, there is a supervisor close to you. They are telling you what to do. Okay. So now this particular example case in the first step, let us assume there is a case of image identification, right? So first picture is shown to you, and there is a question to you asking whether it is a car or a flower. Okay. And initially, definitely, I don't have any knowledge. By looking into some features, I don't know what it is, maybe a color, okay, or something. The learner is saying it's a flower. So the teacher is going to say, no, it is a car. So that means now I made a mistake. I understood that. Okay, who's telling that? The teacher is telling it is a car, and they are also telling me the correct answers, right? So based on this error I made, I will make some adjustments. Okay, this maybe something like, okay, there is a wheel, so I have to say this is a car. Now the next picture is shown. Based on the features I identified in the previous step, I'm saying it's a car. Of course, it's a car. Then next step. Like that, there is a sequence happening. This will be iterative. Again, we will be coming back to step one. Again, the first picture will be shown. This iterative things are happening. Okay, but there is a teacher nearby me. They are telling me, no, this is a car. No, this is a flower. Okay, like that in the bicycle example, do this. Okay, now this is the time to balance your handlebar. This is the time to pedal. Okay, this is the time to apply the brake. So like that, there is a supervisor. Now coming to this reinforcement learning, there is no supervisor here. Okay, now the same bicycle example you imagine, one fine day without the trainer, we'll be taking our bicycle one day, right? So actually speaking, that is the day we start learning the bicycle properly, right? Because there is no one to tell you do this, but we started doing mistakes, right? It is not like we'll be starting with the all proper actions. I'll be balancing all these things will not happen on the first day when you are alone, right? So you are taking lot of actions and there is no teacher or there is no trainer next to you, but the entire environment is there to teach you. Okay, so maybe you will be falling down, there will be more injuries. Okay, there may be some damages. All these things are rewards. Of course, in this case, it's a penalty, right? But penalty is also part of a reward only, right? Maybe a negative reward, I will say, right? But like that, your entire environment is going to teach you now. But it is not going to teach you, don't do this, right? The environment is not saying, don't do this. But the thing is, based on the reward intensity, we ourselves making some corrections. Okay, I should not do that. Okay, when I am about to be unbalanced, I should not pedal more. Okay, I have to reduce my speed. I have to balance my handlebar. Like that, we are taking many actions to learn actually, right? So that is what is happening in reinforcement learning. There is no teacher, but the entire environment itself is giving you rewards and punishments, and you are making adjustments. So these statements are important. These things are very important. Reward. What is the reward? Okay. Because only if the reward is properly defined, then only you will be learning. Otherwise, it is in the opposite direction, right? So in a system, if you are writing the codes for the learning approaches, defining the reward is definitely a key parameter. Okay, if you are writing it wrong, then the entire learning is in the opposite direction, right? So these are some of the terms. Anyway, I'll go through them again. So instead of somebody is telling you don't do this, all these things, you are collecting a reward. Okay. So the reward could be for any action. It may be 100, it may be 50. Okay. Maybe based on this, you have to understand compared to this reward, this action, action A, this action B is comparatively poor. Okay. Maybe for this situation, if I'm taking a different action, it may be giving me a better reward. Okay. So like that only we are learning. Okay, of course, that is how we are learning in everyday life, in everyday activity. Okay, we are learning something. Okay, by getting rewards. So that is what this reinforcement learning is about. So this is what I consolidated here again. Okay, so we are trying to learn some behavior. So this behavior is only we are talking in terms of policies. Okay, or the control actions. Okay, through some trial error interactions with the environment. Whereas previously, maybe you would have tuned your controller using some models or other things. That we didn't tune our controller by interacting much. But in reinforcement learning, it becomes like I'm interacting with my system in the environment. Okay, maybe it includes all the other things, your environmental noise or uncertainties. So your reinforcement learning will be able to learn everything, right? So that is the beauty. Anyway, we'll go through all these things. We will understand them. But the learning happens at this point. You are trying to understand. There is a behavior we are trying to understand by interacting with the environment. Okay, so that is what the objective of your learning agent. Okay, and that learning is happening such a way that I am trying to maximize a numerical reward. Okay, I'll show you many functions. What are the things we are trying to maximize? Okay, so maximization of the reward only is a success of a learning, right? So say for example, the whole day I didn't fall down. I was able to ride my bicycle properly. Okay, I didn't land my foot. Okay, it was completely a stable experience on one day. That is what the maximum reward you receive. So that particular day, whatever you did, maybe you will be trying to do it next day and to the next day like that, right? So maximize the reward. Okay, initially you may be starting with 0. So every day you are learning, slowly you are maximizing, you reach to one maximum point. That is when you will say the training is completed. Now it's time to implement. Right? So this is your objective in reinforcement learning. Okay. So now I told you a lot of terms, right? So they are all going to form the elements of our reinforcement learning. Okay. So there is the agent. So simply I will say I have a PC. Okay. In my PC, I'm trying to write a code so that it is going to learn the control actions. Right. So that is your agent. So the agent is going to have the intelligent program or my training algorithm, okay, which is going to interact with the environment and learn something. Okay. And definitely I need the environment to interact with. Okay, if you are saying I'm working with a control system, which system you are trying to control? Okay, it could be your boilers or your room control system, any control system applications, you name it, that is going to form the environment. Okay, and the policy, as I keep telling you, policy is the action we are taking. Okay, what the agent is going to do to the environment at that particular time. Okay, that is a policy. Okay, so we used to say in English, so this is what my policy is. So what is your policy? This is my policy. Okay, that means given the situation, what is the policy? Okay, so that is the agent's behavior, and this behavior is basically like given the situation I used to say, right? So that means we are trying to map the states and actions, right? So your environment's current situation, we are trying to map with the action. So that is what the policy is actually, right? So given the situation, I'm going to do that. So that means in control system terms, we are trying to map the states to actions, right? And this could be in the form of a lookup table or simple functions. Okay. Mostly today's session, we will talk about more on lookup table kind of approaches. Okay. It can be a simple functions also. So like this, you have a policy and reward function. Okay. A key parameter. So what reward you are writing, reward function you are writing, that is very, very important, right? So based on that only your learning is going to happen. Otherwise, your system is not going to learn. All right. So there are different ways you can write your reward functions. Okay. It could be a straightforward number. Maybe in most of the examples in textbooks, if you are seeing, most of the reinforcement learning books will start with the robot living in a grid world. Okay. So something like a grid case. Okay. Each box represents one state. Okay. Maybe I have something like this is my target goal state. Something like say for my robo, I have my charging station is here, right? So your objective is whenever the robo is feeling low on energy, it has to go to the charging station to charge, right? So irrespective of the position, the robot should be able to go there, right? So that is what the policy is. If I'm present in this state, which direction I'm going to take, right? Whether I will go left or go right or top or bottom or the kind of actions, right? So maybe you can define rewards for each and every state with some numbers. Okay, if my robo is in this state, okay, you are getting a reward. If my robo is here, you are getting a reward. Okay, so if my robo is here, you are getting a reward. Finally, if your robo is able to reach the target, you are going to get another reward. Maybe you can define something like everywhere -1, -1. This is a popular examples again. Okay, everywhere -1. And maybe your target station, if it is reaches there, you can give some +100. Okay, maybe towards the learning is completed, all your whichever state you are leaving your robo, it will try to go towards this target. Okay? That is what the complete learning is. Learn the policy. Right? So I can define my rewards like this also. Okay. Anyway, of course, I'll tell you why this negative things, because only if it is negative, your robo will try to move away. Right? As I keep taking some actions, suddenly when your robo is finding 100, it will try to understand, okay, I should reach somehow this particular state. Okay. Maybe accidentally or during your iterative learning, your robo is finding the state. Okay, so moment your robo some at particular iteration, it finds that in all the future iterations, whichever state you are leaving, it will try to reach there. Okay, only if I put negative in all the other places, it will try to reach there, right? Otherwise, if I am putting +1 here, there is a possibility robo will live in one particular state happily, right? It will keep receiving 1. Okay, every iteration it will add 1 + 1, 1 + 1, 1 + 1 like that. It will be. There is a possibility, even if it is accidentally falling here, it won't think it is a better state, right? So that is why creating a reward function is really critical. Okay, I can define numbers like this, or I can create some small functions also. Of course, most of you on optimization algorithms, you have written the cost functions, right? You would have written them. So like this, I can create some small cost functions also defined for each and every state, right? Anyway, for those case studies, I will show you what kind of reward functions are used. Right? Okay, so now there is also a function called value function. Okay, now this reward, just now I told you, this reward is actually instantaneous. Okay, if I am living in this state, this is the reward I am getting, immediate reward. Okay, so if I am reaching this particular state, immediate reward I am getting. Okay, whereas value function is, I am doing some sequence of things. Okay, say last 2 months, you are doing something every day. to improve your career or improve something. Okay. So every day, whatever you are doing, it is giving you something. Okay. So some particular set of actions, if you are adding something like a cumulative reward. So that is what is represented by this value function. Okay. Say for example, from here, I am creating a set of policies so that my robo will move like this. Okay. So that means in every state, my robo is definitely going to collect some rewards. Okay. So if I can somehow cumulate all these things, I'll show you a couple of functions, how we are going to cumulate this. Okay. So that is what this value function is. So -1, what I showed you here is the instantaneous reward, immediate reward, whereas the value function represents for all set of actions you have taken, okay, from your source state to some target state, what is the entire reward you receive? Okay, maybe I have taken another path like this. For this path, what is the entire reward you are getting? Okay, so that is what the value function is. Okay, so the value function specifies what is good. Definitely, I will say compared to this long route, definitely this route will have a short path. Okay, imagine you are adding with -1 itself without any other features. Okay, so if I am assuming this path, there is -1, -1, -1. So like this, 1, 2, 3, 4, 5, 6, 7 -1s and then 100. Okay, so definitely your cumulative award will be 93 if I take this path. Whereas if I take this path, I'm going through 1, 2, 3, 4, 5 -1s and then 100. So this is 95. So compared to this longer path, this path is giving me a better reward. Okay, better cumulative reward. So definitely my robo will try to take this path. Right. So that is what the value function is representing. Okay. So it is basically a accumulation of reward function, basically on a long run. Okay, I think this explains clearly. Right. So the difference between the reward function and value function. So reward is instantaneous, value is accumulative. Okay, so the cumulative reward. Okay. So that way you remember. Okay. So model of the environment. So if I am working with dynamic programming, definitely I need the model of my system. Okay, whatever system you are trying to control, it could be, say, you are trying to control some boiler with the steam pressure, all these things. Right? So you need to have the model of the system. Okay, so there are model-free approaches. Okay, but whether it is model-based or model-free, you should have some idea. Even in the model-free case, also on a direct implementation, also you have to understand if I do this action, what I am expecting. Okay, maybe in the model, I will be certainly saying this is what is going to happen, right? This is my system. If I give this control action, this will happen. Okay, with the model, you will be able to say that. But without the model, what you will say is, if I do this, I am expecting this to happen. There is a probability term added, right? I am expecting this to happen. Okay, so that is what is necessary for reinforcement learning. Okay, so for all our plans, okay, to map the state and action, we need those things. Okay, I'm not saying this is mandatory, but this can be part of your reinforcement learning. Okay, again, it depends on the kind of problems you are working with. Okay? Whereas all the other things are necessary, it may be present in different forms. Okay, this value reward function is instantaneous. That will be there in any kind of problem. Depending on the algorithm, the value function will take small changes. So in some places, we will say value of the state. Okay, what is the value for that particular state? Like this. Okay, so if this is the policy given, this state is going to take a value 93. Right, like that. We have. So slowly after learning only, you may be converging to this path, right? So like that, it may be defined like this. Or there are cases, anyway, I'll give you those, we'll be discussing those things later anyway, where you have both state as well as action. Okay, so this talks about value for the state, whereas this talks about value for the state given one particular action. Okay, so in that state, if I take that action, what is the value? So definitely both have different meaning, different uses in different algorithms, right? But otherwise, all the other things are definitely part of the reinforcement learning environment. These are all forming the elements of your reinforcement learning. Now, coming to this critical point. Okay, so I told you any control problem, if you can formulate, not necessarily control problem, any learning problem. Okay, I'll say, since I'm concentrating on control system, I'm saying about the control. Otherwise, any learning problem, if you can formulate this as a MDP, okay, then you are ready for reinforcement learning. Okay, you say dynamic programming, Monte Carlo, temporal learning, SARSA, any algorithm you tell me. Right? If you can formulate this way, you are ready for reinforcement learning. Okay. Now, what are the things involved in MDP? We'll see now. Right? So MDP is a 5-tuple problem for control system. Okay, definitely we will say it as it's a tuple. Okay, MDP is a tuple formulation. So there are 5 different elements. So it's a 5-tuple problem. Okay. So the first element is finite set of states. Okay. Now, this is what the environment is saying. So I keep telling you, given the situation, this is what I'm going to do. Given the situation, right? So that given the situation is defined by the state only, right? You can take this example from any board games or our control system examples also, right? If I'm saying I'm working on temperature control system, okay, I should say this is a state variable. Okay, so this state variable, I'm saying finite state. So that means if I'm saying some 5 different temperatures, those zones I'm expecting, right? Maybe I can say something around 10 degrees centigrade, something around 20 degrees centigrade, something around 30 degrees centigrade, 40, 50, like that. I have some finite sets now, right? Finite sets. You imagine in a game environment. Okay, so if I'm playing some chess, okay, I'm roughly drawing something. So based on positions of your various, your elements in your board game, you have different states defined now. Okay, so like this, you are going to have states defined. Okay. Of course, for control system, it is very easy, right? So if I'm saying voltage is present, there is a current I'm going to measure, speed of the motor I'm going to measure, okay, or the output, the temperature I'm measuring, or the current, any humidity I'm trying to measure. Okay, so whatever parameter you are going to measure using your sensors, they are going to form this. Okay, so I'm mentioning discretization is necessary to deal with continuous space. When it comes to control system problem, this is existing. Okay, whereas in the any board game, backgammon or chess, any games, if you are imagining, all our states are discrete. Okay, either whatever elements I'm having, it will be present in this state or it may be present in this state. There is nothing like intermediately it will be present somewhere. Okay, it will be going to one particular grid anyway. Like that is discrete already. But imagine that just now I gave an example, but in real time, my sensor will measure something like 0 to 50 degrees C, right? So which is more continuous. So for learning, it is necessary for you to discretize. Okay. Of course, there are some Q learning approaches with dyno-Q approaches where you will directly tune some neural network. So in those situations, maybe discretization is not necessary. But otherwise, your dynamic programming method, because normally reinforcement learning, that is where we started. Okay, dynamic programming with value iteration, policy iteration, those things are easy to start with. Okay, maybe in your complex systems, when you are trying to start with the neural training, where directly you are going to apply the learning algorithm on the training, you need not discretize that. Okay. Otherwise, discretization becomes necessary. Okay, something like if my system is in this zone, I have to do that. In this zone, I have to do that. Like that. Okay, so for that purpose, discretization becomes necessary. Okay. Anyway, in another session, what I have, I'll be talking about how to handle this situation, right? Because finally, end of the day, my controller is going to take some continuous actions. Okay, so I'll show you those things also. But for initial learning, for the DP algorithms or temporal difference, for those things, I need to discretize my continuous space. Okay, so like this, we are going to discretize. Now, set of states, they are defining the situation, fine, ready. Okay, it is possible for any control application. Now, how I am going to control that? So there will be some actions taken. You can say for controlling the temperature, let us assume I have a heater. For that heater, I'm trying to control the power. Okay, so that means there is a that is the action. Okay, how you are going to control the power. So that is the action, right? So that forms the set of actions. So this is the second tuple. Okay, so given the situation, what I have to do. So that doing part. So there are some set of actions defined, right? So like the way we defined the state variables with discretization, here also, if you are working with a continuous space, you have to discretize. Okay, something like maybe 0 to 10 words, 10 words, 20 words, like that, you have to create some discretizations. That is necessary. Now, the next thing is, I told you about this is what I'm expecting in the real-time environment. Okay, given one situation, if I take that action, what is the probability of going to another state? Okay, something like I'm situating in one particular state S0. Okay, I have some set of actions. If I take some action A0, okay, I may be going to S1, right? But what is the probability of reaching here? Okay. And similarly, when I'm executing this action, what is the probability of reaching another state S2? Okay, so like this, say I'm currently in temperature 10 degrees centigrade. If I increase the power, okay, heating power, what is the probability of reaching 20 or what is the probability of reaching 30 in the next iteration, okay, in the next sampling instant? So that is what defined by the probability. Okay, state transition probability. So how there is a state transition happening, right? S0 to S1 or S0 to S2. What is the state transition probability? Okay. Like in the robotic example also I gave you, if I'm giving the command, okay, my robot to one particular state, I'm giving a command to go north. What is the probability it will go exactly to north? Okay. That is not guaranteed again in the real-time environment. There is a possibility of maybe 90% chance, or in probability terms, I will say 0.9. Okay. There are many other concerns. There may be a wheel slippage, okay, or your entire terrain where you are making your robot to move. It may be rough, and making your robot to go south or maybe south is very bad, maybe east or west. So there is a possibility. I'm saying 0.05%. It may be going to west. 0.05%. It may be going east. Right. So like that, I have some state transition probabilities. So this is necessary when you are writing the cumulative reward. Okay, I told you about the value functions. Right. So for calculating those things, this state transition probability is necessary. Right. And then the reward, the discount factor. Okay, we already talked about the reward function, which is trying to map the states and action. This is the instantaneous reward necessary. And this discount factor, this is one of the important factors actually, right? What this is actually talking about is, in the previous slide, I gave you an example of -1 everywhere. I was adding them directly as it is, right? But when you are writing some reward functions, instead of putting some numbers as negative and positive, I was able to distinguish that. If I'm putting some functions, it becomes necessary for me sometimes to add some discount. Okay. Otherwise, why this discount factor is important is this helps me to converge to my target quickly. Okay. Something like it is falling from 0 to within 1. Okay, that is what it represents. If I am putting 0, this discount factor is 0, that means there is more weightage given to my instantaneous reward. Okay, instantaneous reward. Something like in the grid world, if I'm starting somewhere here, there is more weightage given for my immediate action. Say immediately in the next step I'm going here, there is more reward weightage given to this reward. Okay, but the thing is, after some 5 or 6 steps only, I was reaching my target. So if I am putting 0 here, there is more weightage given here, but there is less weightage for this, right? But if I am giving a meaningful discount rate, of course, it is going to discount all my future rewards. In the next instant, what I am going to get, it will not be -1. Okay, it may be 0.95. Okay, in the next instant, it may be little further less. Okay, 0.9. Like that, when I am trying to discount my future rewards, the probability here is instead of taking more steps to converge, there is a possibility within less steps it will be converging. Okay, whether my discount factor is going to control me, okay, or it's going to help me. Instead of saying control, I would say it's going to help me whether my algorithm is far-sighted or short-sighted. Okay, maybe in the game theory, I can give you an example. Whether I am going to win this game within 20 moves or 10 moves. Okay, this difference can be handled by this discount factor. Okay, so further I discount my rewards, the system will try to do, okay, I have to reach my goal as quick as possible. Then only all these future discounts I can avoid. Okay, so if there is a discount in my reward, definitely it is going to affect my cumulative reward, right? So maybe when you will understand this better when I am showing you the value function equations, right? But this discount factor is mandatory to reduce my future rewards. Okay, when I'm trying to accumulate, it will help me to reduce my future rewards so that I will try to converge quickly sometimes. Okay, so state variables, action variables, state transition probability. The thing is, if I'm having a model of my system, perfect model of my system, state transition probability is 1. Of course, you know that. Okay, because the model is there, I can immediately find out. Okay, if I give this input, this is what I will get. Okay, one-to-one relationship I will get. Okay? But in real-time environment, I'm not sure. Okay, if I give this action, I don't know where I will go. There is only a probability, okay, of reaching somewhere. So the probability of the state transition. I need the discount factor, which is defined like this, something like your learning factor, all these things in many algorithms, and the immediate reward function. Okay, so these 5 things are important to form our MDP. Okay, now, okay, my control system problem, I have formulated this as a MDP. Now, what are the steps involved in reinforcement learning now? Okay, so this is the sequence it's happening. I gave you the elements, right? So now I have an agent. It is observing the input. Okay, definitely it is going to observe the input. Okay, whether in particular state, in the set of states, my current situation, it falls under which case? Okay, your agent is trying to observe. Okay, and it is taking some action. Maybe initially I don't have any policy. I can initiate something randomly. Based on that policy, it is trying to take some actions. Okay, it is selecting the action, and that action is executed on the system. Okay. Once I executed that, I am getting some reward from the system. Okay, or from my environment, I am getting a reward according to the reward function I defined. Okay, so this information is recorded now for the accumulation, for the as accumulated reward. Okay, a value function or anything, it is accumulated. Okay, so this is what is happening in a run actually. Now your algorithm, what it is going to do now is when it comes to improvements. Okay, as a sequence, this is happening. Okay, finally also after the learning, this is what is going to happen. The agent is going to observe, it is going to give some do some actions based on the policy. Okay. So as an algorithm, what your reinforcement learning is going to do is this recording is there, right? So this record, the reward, everything is recorded. It will try to improve this. Okay, so the improvement part comes in the next stage. Okay, so this improvement, based on the improvement only, again we are going to repeat these steps. Okay, so this improvement, how we are going to do these improvements, okay, this comes under 3 major categories. Okay, I can solve this problem, how I can improve my policy. Okay, because that is my objective. So I'll start from some crude policy. My final objective will be to make this optimal. Okay, it is possible in reinforcement learning. I have to make my initial policy to a optimal one. So for that, we have 3 different approaches. All this other small algorithms can be brought into any one category. Right. So this quickly seeing the difference. Basically, dynamic programming requires everything what I defined in the MDP. Okay, all 5 elements is mandatory for dynamic programming. All set of states, all set of actions, all set of probabilities. So probability, if I can properly define only if I have a model, right? Otherwise, probability is a distribution based on the distribution only. If I'm saying this probability is Gaussian distributed, I don't know where to select. It may be 0.9 or 0.91 or 0.85. It could be anything, right? So dynamic programming expects, or in a simple terms, I can say this is model based. Okay. Basically, it demands everything. Okay. I will go through different iterations or go through different states, different actions. Whichever is possible, I will execute on the model, I will learn. Okay. That is dynamic programming. Whereas Monte Carlo and TD, both of them, they don't require model. So the thing is, even if 1 or 2 elements are missing in MDP, they will be able to handle. So most of the time, the missing element will be the state transition only. Okay, whereas because the sets, actions, everything we will have. Okay, only thing is we will face problems with the model only. Model will be there or model will not be there. Right. So mostly they are used in model free. Okay, I'm not saying Monte Carlo cannot be used for model based things. Okay, you can, right? But mostly it is recommended to go for model free approaches. Okay, if when I'm missing something, then also they will learn. Okay. So you can see there is lot of competition between Monte Carlo and temporal difference. Okay. Both are effective. The thing is, in terms of convergence, even though they both will converge to optimal, the thing is temporal difference will be little faster. Okay, little faster. The thing is, what is happening in Monte Carlo is, we will simply say this is episodic. Okay, episodic. So episodic in nature, what it means is, we are talking about policy improvement. Right? So that means after every iterations or after taking some action, I am trying to make some adjustments. Right? So Monte Carlo, what it is going to do is, it is going to make those adjustments after completing one full episode. Okay, this is something like you are planning for your bicycle learning example. We'll go back. For 2 hours, you are trying to learn something. Okay, there are some actions Okay, based on previous days learning, you have some action. Okay, this is what I should do. This is how I should pedal. Like that, you came to some decisions. Okay, in Monte Carlo, what is going to happen is, in that 2 hours, you are not going to make any adjustment. Right? You are not going to make changes to your policies. Okay, but what you are going to do is, I end up that 2 hours. After coming home, you are going to analyze. Okay, what are the things went wrong? Okay, I did this. There is a problem. There is a problem. Okay, I have to make this correction. That is what Monte Carlo is doing. Okay, it is episodic. It completes on episode. So that is why most of the game theories they will be using it. Okay, which are episodic. Something like in the chess game, you are starting somewhere. Finally, you are winning. This is one episode. Okay, something like your maze solving robots. Okay, for solving a maze, you are starting from some location. Okay, there is full episode that covers starting from that location, reaching your destination, or coming out of the maze from the other direction. Okay, so this is one full episode. Like that, if you are working with some episodic tasks, you can go for Monte Carlo. Okay, but whereas temporal difference, this covers all the benefits of Monte Carlo in real-time learning, but also it takes some actions. There are some adjustments made based on the something like one step look ahead, they will say. Okay, so whereas this is like full episodic look ahead, whereas temporal difference, if I am working with one step look ahead, that is what is represented by TD0. Okay, if you are searching for temporal difference learning, most of the articles you will find based on TD0. That means it is like a one step look ahead. Okay, based on that difference, it will keep adjusting the values, whether it is a direct value function or the state action paired value function. Okay, so this is something like bootstrapping. I'll show you the equations also. Okay, so this is like a shortcut computation for Monte Carlo. Okay, maybe once you are completely learning, both will converge to the optimal solutions only. But the thing is, the way of learning, there is something quicker. Maybe if I'm plotting something like the cost function, temporal TD may be learning like this, whereas Monte Carlo may be learning like this. Okay, that is what maybe you can expect. Okay, otherwise both of them will reach the optimal. That is not a problem. The thing is, sometimes in real time, I want something to happen, something quickly, right? So for those type of situations, maybe you can go for temporal difference learning kind of cases. Okay. Okay. Now, coming to this dynamic programming. Anyway, I'm going to discuss about this dynamic programming based cases and one temporal difference based case. Okay, for understanding the case study, everything. Okay. So dynamic programming is definitely it's a classical solution. Right? So it requires the complete and accurate model. Okay, as I told you, it requires all the information. Okay, only if I have all the information, I will learn. That is how DP works. Okay, in a game of chess also you can do that. Okay, even though in real time Monte Carlo is more successful. Just for example, I am telling you, in a game of chess game, definitely you will have all states. If I do this action, I know where it will go. Okay, where my bishop will go, where my queen will go. Like that, I know where my pieces will move. Right. So like that, I need the accurate model. Okay, and the popular method here is, I told you I'm starting with some random policy. Right. So for that policy, you are going to evaluate. Okay, I'm going to evaluate by calculating the value function. So just now I gave you an example, taking one path, which is a policy. Okay, that gives me 93. There was another policy which gave me 95. So like that, I am really going to evaluate the policy. Right, and of course that policy. Maybe I gave you that example on the grid world. Okay. Okay, let's say I'm starting from here. There is a path like this. This is a policy you are saying, right? This policy, actually, this is for all the states. It's applicable, right? There will be a policy. So for this state, this is like go up. So for this state, this is like go right. So for this state, this is like go down. Okay, for according to this policy. Okay, for this state, the policy is go right again. So for this state, the policy is go up. Same way, there will be something defined for all the states. Okay, go left or go down, like that. There will be something defined. Okay, when I'm roughly initiating my policy, it will be definitely bad. Slowly, you are going to converge so that you will maximize your reward. Okay, so like that, you are starting with the policy. You are going to evaluate this for every state. Every state you have to do the evaluation. So we evaluated for this state, and we in that previous example, we came out to be something 93. Okay. So like this, I am going to evaluate for every state. Okay, that is what the value function is. So once I evaluated that, I will try to improve that. Okay, now slowly I know from this state, when I'm going there, I was getting something maximum. So maybe this particular state will think about, okay, my agent will think about, instead of going here, how about taking action and go here directly? Okay, because if I take another 2 steps, there is a discount also happening. Okay, negative reward is there. So definitely I'm ending up with a poor reward, cumulative reward. So instead of that, why not I will try some action to reach here? Okay, definitely there are two sampling steps you are reducing, your cumulative value is increasing. So that is what the policy improvement is talking about. Okay, I will try to improve this. Maybe in the initial stages, your policy may be something like going this side for this state. Okay, I'm not talking about those things anyway, but finally towards the convergence, you will become optimal. Okay, so every step there will be some improvement. Okay, sometimes I take bad actions and luckily it may be working. So I will be repeating those actions for some years, but suddenly you are realizing, okay, this is a bad action, what I was doing for years. I have to do this in this situation. Okay, so like that, there is an improvement. It may be happening anytime, right? So we are going to evaluate the policy, improve the policy. So this is what we are going to repeatedly do. So this is a popular method of dynamic programming. So for that updation only, I told you about, this is talking about expected. Okay, so the policy is mentioned by some pi. Okay, I told you for each state, go up, go left, go right, like that I mentioned, right? So that is the policy function pi. So for that particular policy, okay, so for any current state, the value you can find out expected immediate reward. Okay, if I'm saying from this state, I am going to take an action like this, that means what is the immediate reward you are going to collect from here? Okay, that is what it talks about. Okay, so from some ST, I have taken some action to go here. Okay, so I'm getting an immediate reward, and from there onwards, there is a sequence. Okay, so all these things will be accumulated here. Okay, discounted remaining rewards. Okay, anyway, I'll go show you the expanded version of this. This is the shortest version. Okay, so this is discounted. So there is an expectation. So this is what you are trying to increase. Okay, so that finally, once this increasing is stopped, that means you converge to some optimal policy. Okay, you are improving, evaluating, improve, evaluate. So this is the method you are doing in dynamic programming. Okay, so I think I gave you this. This is what we discussed. Agent, it takes action. This action is based on the policy pipe. Okay, from the environment, I am getting the reward, and also I am going to observe the states. Okay, I have some sensors placed to measure the state variables, all these things you will see. Right? Okay, now coming to the discussion, what we are doing now. Right? So I am starting with some state S0. Okay, let us assume there is a my sensors are saying that there are some 2-3 sensors. They are defining this is the current state. Okay, this is your current state, and based on that state, your system is taking some action. Okay, your controller or the system is your controller actually. Okay, it's not the system, it's a control. So your controller is taking some action A0, and that A0 is doing a state transition going from S0 to S1, right? And you are collecting a reward R0. Okay, so action is A0, and because of that, you are receiving some reward R0. And during this process, you are identifying from S0, you move to S1. Okay, now the sensors are telling this is my new state. So from S1, I will take another action, another reward, new state. Okay, so this is what continues, right? This is what is going to happen continuously. Okay, you may be saying it may be terminated with some target. Okay, this is what our final control objective also. Right? So in the game plan, you can imagine you are starting from something, you are finally reaching a winning state. Okay, your robot also, you are starting somewhere, finally reaching the charging station. Okay, so this particular loop will end with the target state, right? It may be sometimes infinity, all these things are there. Okay, for control system also, you can imagine this way. Right, what is our target? If I'm saying this is what the speed should be, okay, given the current speed, you are taking some set of actions to reach that speed. Okay, for your motor. Okay, given the current temperature, you are taking some set of actions to reach the target temperature, like that. Now, definition of this value function and policy function. Okay, see here, for all the states, okay, given some policy. So, okay, based on the policy, we are doing some action, right? So I took A0 and A0, A1, everything based on some policy, right? Okay. Now, for that case, given, okay, I'll start from here. Given my current state is S0 and pi, there is the action taken pi. Okay. If this is the for this situation, you are getting an immediate reward plus discount reward from the next state, further discounted from the next state. Like that, it is going to happen continuously. Okay. Of course, plus there will be gamma cube reward coming from state 3. Okay, this is what I told you in that grid example. This is -1. It may be 0.99 times -1, and it may be 0.99 square times -1. Of course, this will be lesser, right? Compared to 0.99, this will be lesser. So like this, you are going to discount all your future rewards, add it, and this is what you are expecting. Because again, with the model uncertainties I'm talking about, there is a probability of going from S0 to S1. There is a probability of going from S1 to S2, right? So that is why there is a word E included here. Expected sum of discounted rewards. Okay, so this is what this value function is represented. Okay, expected sum of discounted rewards. Right. So this is what I am going to calculate for every state. Every state I am going to do this. It is not only for S0, even for S1 I will do that. For S2 I will do that. So for every state we are going to calculate and come up with this function. Okay. So if I'm saying there are 10 different states possible, then we will have all these 10 values. Okay, 10 values will be there for the value. Okay, if I'm saying there is a grid of there are 2 state variables x1 and x2, for every combination I will have some value. Okay, so this is what I'm going to calculate. Right. So once I calculated, evaluated my policy, there is going to be a new policy, right? So based on which is maximum, right? Based on that only I'm going to take action. So something like from this state, if my system knows surrounding all, there are how many? There are 8 different states around this. Okay, for this state. Okay, so if it is trying to maximize the reward, it will try to go to the maximum point. Okay, in that particular situation, if this is what is maximum, then your system will try to take the action to go left and go here. Maybe at the end of the convergence, if this is my target, it may be taking action to go here or go there. But in that particular iteration or in that particular episode, based on the maximum value only, you are going to define your new policy. Okay, improvement for the policy. Okay. Maybe in the next iteration, your value may be going here. In the next iteration, it may be going here. Okay, so like that, new policies are defined based on the existing value function. Okay, so this is what the critical point in reinforcement learning. Okay, this is what we are going to code now. Okay, so your objective is maybe every time you are having some value. Okay, maybe initially you started with -1, then it was minus 5 point something. Like you keep increasing. Okay, maybe in the positive direction also it may be increasing because it is touch. Sorry, I started with 93, right? So maybe that was your final value. Slowly at one particular point you are reaching 94. Compared to previous action, this policy is better. But finally you are reaching somewhere 95. Okay, this action is better than that. So like that, your objective will be to reach the get as much reward as possible. Okay, I have to reach something bigger. Maybe I started with 93, but I should try to reach 95 in that example also. Okay? Maybe in real time the numbers will be bigger, but this is your smaller objective. You have to maximize that reward. Okay, if I can maximize that reward, that is what is represented by this Bellman equation. Okay, this was defined in 1950s, early 1950s, right? till they are valid in most of the game theory, dynamic programming, all our reinforcement learning applications. This is very powerful, right? So whatever we discussed previously, same thing is mentioned here. Okay. But the thing is, previously we just talked about the value function, policy function. Here we are more talking about optimal value function, the converged functions. Okay. So here also we are talking about the immediate reward. Okay. In any state, it may be S0, S1, S2, anything. For that particular state, there is an immediate reward and then maximum of all the future reward, discounted, probabilistically transited states. Okay, we discussed about from S0, it is going to S1, it is going to S2, like that, right? Similarly, it includes what is the probability of going there, right? So that also should be accounted, okay, so that it becomes the optimal policy. So it includes all the uncertainties now. If I'm saying there is a uncertain system behavior, there is a sensor noise, there is an ambient disturbance, whatever you say, your system will learn that. Okay, that is why this reinforcement learned control can be a robust controller also. Okay, not only optimal, it can be robust also. Correct. So based on that value function, the argmax function. Okay, so this is again when you are talking about a set of argument from there, taking a or set of an array. Okay, from set of an array, selecting a best one for all set of possible actions. So the argmax is a important function for you for identifying the optimal policy now. Okay, now we are talking about this is the optimal policy. From controller point of view, this becomes the optimal controller. Okay, if I can say this, I can create a function like this based on the value calculation and this one, whatever I'm finding here will be the optimal controller. Okay, there is a guarantee definitely. Okay. So these equations basically represent the Bellman equation. Okay, of course we have to go back to history for writing these equations. Whatever updations you are doing, there are some small changes only combined in that Bellman equations. Right. Now we'll talk about this policy iteration. Now we are going into the real algorithm. What is happening? We talked about policy evaluation, policy improvement, everything. Right? So this is what the algorithm is. Okay, in DP dynamic programming, we have two things. One is policy iteration and value iteration. So in policy iteration, what is happening is this we discussed already. I am starting with some policy. For that policy, I am going to calculate the value. Okay, how I will calculate the value if I evaluate, and then I will improve my policy. Okay, or I will select a new policy. For that, again evaluation, improvement, evaluation, improvement, like that I will go. Finally, I will converge to something. Okay. Of course, in the previous step itself, there is a pi star indicating your policy has converged. Okay, if there are no further changes coming in the value or there are no changes in the policy, then you can guarantee my policy has converged. Okay, my control actions are converged. Okay, go up, go left, everything is converged. Okay, now coming to the algorithm, you are initializing with some random numbers for all the state variables. Okay, if I'm saying there are 100 states, for all 100 states, okay, I'm not talking about 100 state variables. Say for example, in a room temperature control, let us assume I have a temperature and humidity parameter. Okay, temperature I have discretized into 10 samples. Okay, 10, 20, 30, like that. I have some 10 samples, 10 discrete values. Similarly, let us say humidity also, I have 10 different samples or discrete values I'm having. So all combinations, if you are seeing 10 by 10, right? So there will be 100 different combinations possible. So for all these 100 different combinations, I have to define some value. I have to initialize with some random values, right? And similarly, arbitrarily, I have to take some initialize some policy. Okay, again for all states, for all these combinations, say for example, based on the temperature and control, you are trying to, there is a air conditioner, you are trying to control the power delivered to that. So that power also I have to define now for all control situations. What should be the power? Like that. Okay. So this we are going to do for all the state variables within the larger set 100. Okay. Okay. Now for we are going to do the policy evaluation. Okay. So policy evaluation, we already initialized the values. Let us assume it is all zeros. Okay. I'll move the zeros here, and what we are going to do now is, I'm for that particular policy, I'm trying to collect for each state. Okay, for each state, I'm trying to execute this policy. Okay, I will take that action. I will try to collect the immediate reward and all the future rewards. So future rewards, definitely in the first iteration, it will be poor. Right? That is why there is a repeat we are doing in the outer loop. So this is your major loop outside. Inner, you have it for all states. Okay. So for all states, I'm going to calculate the value. Okay. If you are observing there is no change, definitely in the first iteration you started with 0. This particular difference will be large. So I'm going to update it. Fine. Okay. Now, definitely in the first case, this is not small. There will be large change already happened. So I have to repeat again for all states, again calculate. All state, again calculate. So here, imagine, just remember, we didn't update the policy now. For the same policy only, we are trying to calculate the value function, and it is not simple. Okay. Why it is not simple is, let us again go back to the grid example, which is easy to understand. Let us assume initially you have a policy something like this. Okay, some policy like this to reach the target. Okay, to reach the target, you have something like this. Okay, this is my target now. Okay, now in the first iteration, what will happen is based on the immediate reward, only this state would have updated, not everything. Right, based on this policy, only this is taking you to the target. So maybe in the first iteration, this is the only value updated. Okay, otherwise everything will remain from -1. Okay, now in the next iteration, whichever actions taking you here, maybe these two people, these two states would have updated. In the next iteration, this would have updated. Okay, in the next iteration, all these other things would have updated. So like this, it takes more time to converge. So that is why inner loop is running. Okay, that is because there may be a doubt like for one particular loop with all states, is it not possible? No, it's not possible, right? This is what is happening. Whichever is taking you closer to the target will be updated first. Okay, everything else will take some time. Okay, so that is why we are doing it repeatedly till these values of each and every state is not changing much. We are doing this iteratively, right? Once this evaluation is completed, I'm going for the updation now. Again, updation is also cyclic. So for every state, I have to find out, okay, based on the previous experience, what is new. Okay, instead of going to here, shall I go to this side? Shall I take this action? Okay, so like that, you are going to make some changes based on the RMath function. Okay, this you are going to do, and if you are going to check whether there is improvement or not. Say previously you have this policy. At the end of this improvement, if there are changes, then that means your policy is not converged. Okay, if the policy is unstable, okay, you need to go to step 2 again. Only if your policy is stable, then only you are stopping. Okay, if there are no changes in the policy, you can stop. Otherwise, go to this step because you improved the policy now. Just now you modify. For this modified policy, again take the value evaluation, then come to improvement. Okay, so this is what I represented here. Okay, so value iteration, it involves a lot of iterative steps. Okay, of course, this is also straightforward, but it takes more time for the algorithms to give you the final solution. Okay, so that is why compared to policy iteration, value iteration is possible for popular, because you can see here value iteration there. What I did is I modified the policies and then we waited till it converges, right? Now, in value iteration, what we are going to do is in the inner loop, okay, you can see there is no complex outer loop, secondary loop, all these things. Okay, so there is a repeat. Of course, this is a major loop. We are going to wait for the convergence. For each state, okay, I am going to take the action directly. Okay, if I'm saying A is defined with some, say there are some 4 actions I'm having, like this 4 actions I'm having. For any particular state, I will implement all actions. I will implement A0, I will execute A1, I will execute A2, okay, I will execute A3, and I will observe where it is taking me. Maybe A0 is taking you to S1, this is taking you again to S1, okay, this is taking you to S2, this is taking you to S3. Okay, based on that, I will update my value function, right? From S0, if I take A0, I go to S1. Based on this set of pair, I'm having one value. So based on this pair, I have another value. Okay, based on this pair, I have another value. So like this, for each and every state, I'm going to execute all possible actions and update this value function. Okay, and if this value function is converged in one particular iteration, I'll stop there. Okay, otherwise I'll repeat this. Whatever converged here is the value. Optimal value is converged here. Okay, so I can, from this optimal value, I'm going to directly say this is what the optimal policy is. Okay, there is nothing like policy evaluation, because see, for every state I am taking all possible actions. So that means there is a policy evaluation is happening. Okay, but not the entire policy action. This is one step policy only is evaluated here. Okay, it is not like we are completely eliminating the policy evaluation. It is happening, but in a different view. Okay, so every action is evaluated in almost every step. So that is what is used for the convergence. And finally, 5-star will give me the optimal policy. So compared to policy iteration, definitely your algorithm will run quickly. Okay, so the convergence, everything may be faster in the value iteration. Right. Now, coming to the temporal difference, as I told you, this is more related to model-free approaches, right? Something like bootstrap. Maybe I'll show you the equation for update that from there we'll discuss, right? Okay. Just now we discussed about the value updation. So in the policy iteration and value iteration, the value update, if you're seeing, the value was updated based on the instantaneous reward and the discounted future rewards. That is how we updated the value. Whereas temporal difference, which is almost episodic, but not completely. So it is based on what I found here is TD0. As I told you, it is a one-step look ahead. Okay. So what we are doing here is, you can see value will be updated based on the, okay, the current values to be updated. So in every loop, there is going to be a value, existing value. This is the existing value. This is the new. Okay. So the old values to be updated based on one particular step size. So this alpha is going to define the step size. How much bigger I'm going to modify my values. Okay. For that, we are going to use the immediate reward which we are going to collect. Okay. This is the immediate reward I'm getting from the next sampling instant. Okay. From S of t, I'm taking some action going to S of t plus 1. Okay. And from there, I'm collecting some reward, right? Yes, from S of t plus 1. Okay. So for that S of t plus 1, okay, there is a reward it is having. And that reward I'm going to discount. Yes, of course, we are using the discount reward again here. Okay. But the thing is, I am working based on the difference it is having with the current value. Okay. So this entire thing within my parenthesis, squared parenthesis, is talking about the temporal error. Okay, so this is what the temporal difference learning, based on the difference within one step. Okay, one step ahead it is looking. Now you may be asking what is the difference now with the Monte Carlo. So I'll try to write here. So if you are using Monte Carlo, this updation for the current state will be based on the, of course, it is the update for the using the old one plus alpha times. This is the grand return minus V of ST. So this is the basic difference actually comparing Monte Carlo and temporal difference. So this is looking into one step ahead and it is making some updation, right? Whereas GT is talking about the complete return. Complete, as I told you, the example, I am doing a training for 2 hours. After reaching home, I am trying to evaluate today what happened for that entire 2 hours. Based on that, I am updating. Okay. So, like that, of course, in that 2 hours, you would have experienced many things. So, using everything you are updating. So, definitely you are going towards the convergence only, but the updation is not happening periodically. Okay. Whereas this is one step ahead, this is periodic. Okay. So when you are writing the code, this is what is going to differ. Otherwise, if you are writing a code with the model, everything, you will observe, okay, both are converging, you are getting the same optimal result. Okay. Maybe when you are implementing on the real-time environment, the way it is converging will be different. Sometimes you need a faster convergence so that you are, say, in a bicycle learning experience, maybe it is not a very costly thing. But imagine in the maybe in a game theory, all these things also, it is not very costly. But in an industry environment, let us assume you are working with the learning in the real time itself. Okay. Sometimes if your convergence is slow, there is a possibility you are taking wrong actions. You keep taking wrong actions. Okay. Which will be definitely costly for your organization. Right. So you would have taken more wrong actions in the process of learning. Okay, so those things sometimes it is necessary for you to avoid. So in those situations, temporal difference will be a better option. So this is what the algorithms look like. So as I told you, this is the only difference. Otherwise, this is also the same value iteration. You are starting with initialization. Okay, and for all actions, you are for all sets, your set of states, you are going to take the actions, update the value, converge. So once they converge, you will be able to find the best action using the Rmax function. Okay, Rmax of the PFS you can take to find the best pause. Okay, so that way you are updating your value. That is what is going to differ. Okay. Right. So now we'll come to the case study now. Since my major domain is on process control and instrumentation, we tried it on the interacting tank system. Maybe your systems, whatever systems you are having, you will be able to formulate this into MDP and you can execute that. Okay. So now for this system, we have two state variables. As I told you, we need the state variables to be defined. Right. So H1 is one state variable, H2, the level, liquid level in the systems. Okay. And action is the flow rate. Okay. Of course, written here, right? Flow rate. Okay. This is the only action taken on the system. Okay. So you have the model. So ODE models we used for simulation. So like this for your system also, you will have any dV by dt or di by dt. So like that, you will have your own system models. So those things you can use. Okay. So I have the model, I have my states defined, I have my action defined. Okay. Now for the MDP preparation. Okay. So what we have is both the tanks are having with the assumption 0 to 10 meters in height. Okay. And we are going to discretize them into 10 steps each. Okay. Of course, if you are using MATLAB or Python, whatever code you are writing, you have options like to segment your ranges. Okay. Lint space, like that, you have different commands to separate that. You can try those things. Okay? Similarly, the flow rate also, I have 0 to 20. So this also we are defining into 10 steps. So now, of course, you can see this combination. Okay. So H1 and H2, if you are combining, and 10 plus 10. So there are 100 different state combinations I have. Okay. And for all these things, I have 10 different actions to take. Okay, this is the way I'm preparing my MDP. Okay, we are preparing for the MDP. Okay, so we of course used a value iteration with a gamma of 0.99. And as I told you, this reward function is important. Okay, I gave you an example with -1, all these things, right? So here, the way we define this, of course, when we are talking about control system, I will say this is my desired value. Okay, something like I will say I need my level 1 to be 77.5 meters, something like that. Okay, I will say. So that is your H1 desire, right? So in our objective speed controls also, I will say this is my target. Okay. So we define the reward function. Mostly this is what popular in for control applications based on the equilibrium distance. Okay, of course, norm we will say, right? If I'm having more state variables, you can say this is the norm. Okay, the equilibrium distances basically, right? So based on the difference between your current state and the desired, we are creating this reward function with some magnitude. So this is just only to show you the value with a some factor of multiplication. I can say -1 also because your learning is not much affected because of this number. Okay, just for all your observations and visualization, this will be useful, right? So for that we are having 100, but of course this -1 by now you know, right? Why this -1 is important, right? Because the -1 only was pushing me in a shorter path. Okay, because longer path was giving me 93, shorter path was giving me 95 as the accumulated reward. So that is why I have the negative. Just imagine in that case also for the target we have given something like 100, right? So everywhere we mentioned -1. For the goal state we have given 100. If you are planning for some states to be avoided, let us assume you are using this robotic application for cleaning your room. You have to say this particular zone you have to avoid. Say you may be having your sofas or your chairs or somewhere. That particular state your robot should avoid. You can create a -100. Okay. Whereas -1, your robot can go through. It can stay, but it has to leave. 100 is the target, but -100 is the state it should avoid completely. So like that you can plan. Right? In the control system also, you can define some constrained optimization control problem. You can define something like this is to be avoided like that. Okay. So this with that 100, you can imagine once I reach the target, I was getting 100 there. Just imagine the situation here. Once I reach my desired value, this becomes 0, right? So your reward will be 0 compared to all the other states where I received -100 times the difference. Okay, I'm getting 0, which is definitely a higher value. Okay, so that is why in the graph I'll show you everything you will see negative. Okay, but your biggest reward your system can get, immediate reward your system can get, or the agent can get is 0. Right? Of course, compared to other states, it's a better reward. Okay. So this is what we achieved here. Okay, your state variables H1 and H2. Okay, on these two axes. As I told you, the value function -2 and 2000, -2, 4000, -6000. So this is how it will converge finally. Okay, this is how it will converge. Okay, because our objective here was again. So level in tank 1 should be 8 meters. So you can see here 0 is starting here. Around 8, this is maximum. Okay. Of course, the values are low here, slowly rising, and of course, after that it starts tipping. Okay. So this is how your value function will converge. Based on your desired location, your value functions will converge. Okay. And this is another graph where I showed you with finer discretization. Okay, here we discretize the H1 into 10, H1, H2 into 10 levels, right? So like this discretization. Here we discretize into 15 and 15, and the actions into 25. The curve is little smoother compared to this. Okay, if I go finer, definitely my curve will be smoother. But in reinforcement learning, popular term again, curse of dimensionality. Okay, in most of the machine learning also you have this problem. If my dimensions are increasing, okay, your learning will take more time. Okay, there is a curse of dimensionality. Okay, so that problem you will face. So because of that, you need to avoid finer discretization. Okay, because when this is taking some 2 hours to convert, of course it takes 10 minutes to convert. It depends on the system model also. Okay, for example, I'm saying if this is taking 1 hour to converge, there is a possibility this will take 3 or 4 hours to converge, even though the small number is different. Okay, so like that, that is what curse of dimensionality is. So these are all the value functions it learned. Based on that, when you are trying to find the optimal policy, so this indicates if this is your H2, this is your H1, this is what should be the flow rate. Best policy means what finally? In that particular example, the policy is talking about what flow rate to be given to the first tank, right? So this is what it is learning. Okay, you can since it is 2-dimensional, I'm able to visualize this like this. Maybe you are working with a single dimensional problem. Anyway, I'll give you another. Our Q learning is on a single dimensional problem only. Okay, so you will have everything like if say in my X, this is my X desired. Your value function may be converging like this. Okay, so based on that, you will be saying this is what the action I have to take like this. Okay, maybe the action may be something like this also. Anything, it depends on the system you are working with. Right? So this is how it may look like in a single dimension case. Of course, in 3-dimensional, if you are working with the 3-state variables, we cannot visualize that. Okay, so 2-dimensional, we are able to visualize like this. Okay. Of course, responses, we are not seeing much difference because both cases were almost converging. Maybe if you are working with a different complex system, that maybe the final responses may be a little different, but otherwise both of them are similar. But the major difference we observed in the action taken. Okay, because here we are discretizing into 10 actions. Here we were discretizing into 25 actions, though there were some other steps also possible here. Okay. So that is what is difference, right? So if I'm saying I'm going to feed some voltage from 0 to 1, okay, saying I will be going to either 0 or 1 or 2, like that only I'll be able to give. It is different from saying I can take 0, 0.1, 0.2, 0.3. So that is both are different. Right? So there will be more smoother control actions if you are having finer steps. But the thing is, your learning will take more time. Okay, if you have time to spend with your MATLAB or Python to sit your system while it is converging, no issues. Okay, you can spend more time. Right, now with that, we are concluding the model-based study. Now I'll give you the model-free RL approach, Q learning. So here also the same things are happening. You are going to take the actions. But the thing is, in those situations, I gave you a system algorithms like for all possible states, you have to do that. But in real time, you cannot do that. Okay, so my system may not be experiencing all possible combinations, right? Okay, in H1 and H2 previous example also, I told you 100 different state combinations possible. Mathematically true, but practically it's not necessary. I may not be encountering some particular state combinations, right? So in those situations, how we are going to learn? Okay, there is a possibility I may be never faced one situation. So that means what? Your controller never learned. Okay, something like in your bicycle learning also, from the first day onwards, if you never fell down, you would have never learned, okay, I will be falling down, right? You would have learned only to ride the bicycle. So like that, there are situations possible. Okay, so for those situations, you should be able to handle. Okay, so the basic differences, I think I can quickly go through and end up today's session anyway. Right? So the Q essay, if you are seeing, as I told you, there is B of S we discussed till now. So in Q function, we have for each state, for each action, what is the value? Okay, so for S naught, if I take A naught, what is the value? Okay, for S naught, if I take A1, what is the value? So like that, we have this Q function. Okay, so that Q function we can update like our temporal difference learning. Okay, of course, if anybody already have exposure to other algorithms This is very close to SARSA-like algorithm. So you can, anyway, if you're having time, you can Google it, SARSA-based robotic applications. So the main difference is this maximum term will not be there in the SARSA algorithm. Okay. In Q learning, you will have this max. Okay. It's talking about the maximum of where I have the next step maximum. Okay. To that, based on that, we are going to update. Okay. It is not simply taking from the next state. Best next state. Okay. So like that. Now, this is what I want to spend more time now, because I told you the actions you are going to take now, not on all states. Okay. Given the situations you are measuring in the real-time environment, I'm not talking about the model-based. Now, shift our situation to a real-time situation. Okay. So in the real-time situations I'm working, okay, I cannot explore all states in that particular step of learning, in that particular sampling instant. Right? But the thing is, still I have to take some action. Okay, maybe I started with some random policy defined to me. Okay, and from there I'm going to take definitely fine. But still, I told you about I would have never exposed to one particular zone. Okay, but that zone is where I have my objective is something like in optimization problem. We will say I have the global minima, local minima, all these things. Okay, so if you never exposed to global minima, you will be happy with your local minimum, right? So you will be staying there. So there should be something happening so that you will be coming out of your local comfort and you should go for the global comfort. All right. So that is what the actual learning is. So for that, I have to do something so that my system will get exposure to some unknown states, occasionally at least. Right. So that is what this exploration and exploitation is talking about. Okay. So exploitation is more about, okay, somebody told me you have to do these things to do, okay, to maximize your reward. So I keep trying these things only in my states, if this is the state, this is what I have to do. This is what my lookup table is saying. This is what my teacher told me, like that, right? So this will definitely give you rewards. You will be able to maximize those rewards. Everything is possible. Okay. But the thing is, occasionally I am trying to explore. Okay. Exploitation is doing what you already know. Okay. You keep doing what you already know. But exploration, occasionally I am trying to do something new. Okay. So this might have given you a new experience and you identified, okay, this particular area is fine. I can take this path. Okay. Or in terms of investment also, you can say, if I do this investment, this is giving me better profit. Okay. Maybe you would have last 10 years, you invested in one particular, maybe a stock or something. You have your incomes, you invested somewhere. Okay. But suddenly you find, okay, if I do that, what happens? You identify, okay, there is a new source. This is better. This is safe. All these things. There may be many parameters. So based on that, you can come to a new conclusion. But of course, exploration, I'm not saying it is always success. Failure is also possible. But still, you may be getting an option to come out of your local team, right? So like that, this is the trade-off, right? But both we cannot do simultaneously. If it is a model, I can do simultaneously. But in the real-time environment for that particular state, okay, living in that state, I cannot repeatedly do both of them. Okay. Again, it's not guaranteed that I will be coming back to the state again. Okay. So I have to balance this exploration and exploitation when it comes to real-time learning. Okay, a really critical problem. Okay, so you have to maintain some trade-off. This is the trade-off we are talking about. You have to balance it. Okay, so for that, what is the solution? Okay, we have this epsilon greedy search. Okay, so this is nothing but you are going to create a random number. Okay, so if that random number is something like less than 0.8 or more than 0.8, within 0 to 1, you are creating a random number. Okay, if it is less than 0.8, I will do something. If it is more than 0.8, I will do something else. Right? So like that, you are going to do some greedy search. Okay. So this is very critical when you are going for real time. Okay, so something like, as I told you, I can say 0.8 and this is 0.2. Okay, so 80% of the times, maybe exploration I'll give less, exploitation I'll give more. Okay, because already something I know, I will do more times what I know already. Right? Maybe I'll try to explore twice or once in 5 times, like that. Okay. So 20% of the time I will try to do something new, randomly select from the action I will execute, or 80% of the time I will say there is a policy, from that policy I will take. Okay. So exploration and exploitation. Okay. So select something random or select which is already known to you. This is the only difference I want to tell you today. Okay. So like that we are trying to balance something. So this is the Q learning with greedy search. Okay, so this update, we discussed all this value iteration, everything. So this is the way we are updating the Q function. Instead of updating the V function, we are talking about the Q function. So in that Q function, previously in all the previous algorithms, I told you take all actions. So for all set of states, take all set of actions and find out. Okay, but here I'm going to say, for that particular state where you are living now. Okay, so for that state, choose the action using epsilon greedy and take action, update your queue. So how I am going to take the epsilon greedy? This is the epsilon greedy. So action selection. I created a separate loop for that. Right? As I told you, simple case. Select a random number between 0 to 1. If that number is less than that epsilon, if I'm saying 0.8, okay, random, okay, so say less than, okay, so 0.2 I'll say. Okay, if the number is less than 0.2, take a random action. If the number is more than 0.2, that means 80% of the chance, right? So take the maximum of the existing policy, okay, and give that action here. Like that, the action selection, we need to be a little more careful, okay. And this, of course, in real time, we implemented on our indigenously built ball and beam system, the case study. Most of you know this is the one of the benchmark problems to locate the, you to position the ball on this beam. Okay, ball and beam control. Anyway, quickly go through those things. Right. So this is how we discretized. Okay, 1 to say 8 centimeter as state 1, 9 to 16 centimeter state 2. We defined 5 different states. Okay, of course, since it is real time, we created the window size large. Okay, maybe you can try smaller things. Okay, where it may take little more time to converge. Okay, little more time to converge. So our goal state is 20 centimeters. That means it is somewhere here. Okay, I should reach here. And beam angle also. So how we are going to tilt the beam. Okay, in the previous slide, you can see how we are going to tilt the beam. Okay, using this motor. Okay, so that also we divided into 10 segments of each 4 degrees. Okay, for that angle. So this is the set for actions, set of states. Okay, your goal state. Based on that, the rewards are defined. Okay, during the learning phase, this is what we observe. Initially, we started with random policies or nothing learned. 10th iteration, we observed after some 300 samples, the ball was reaching the target state, it settled there. Okay, but before that, there were a lot of oscillations. And trial number 15, actually, each trial has 1,000 iterations. Okay, it is not like one trial within 10 trials. That means it takes 10,000 different actions. Okay, it happened already. That's right. Okay, after 15th trial, we observe it almost settled. Okay, this is the trial we are showing. The final learning, this is how it learned. Okay, what beam angle to maintain, all these things. So I mentioned the word here, optimal policy, approximated value. Maybe actually on 4th, I will be taking another session. So this is the initial idea for what we are going to discuss there. Okay, you can see this is here the policy is discrete, like it is not smooth basically, right? It's more rough. Okay, so here it is more smoother. So this may be used for the continuous control. We are talking whenever we are talking about control system, it is definitely continuous, right? Maybe you will say on, off, step control, all these things are there, but mostly we will talk about continuous state, continuous actions. Okay. So here also you are talking about, we are seeing discrete things. So here it is continuous. So this is the Q function learned. Okay. So like these things, anyway, why we need this approximation, all these things we will talk in that session. Okay. So before I conclude, I just want to mention some reads for you. Of course, these are all some lectures. There are a lot of YouTube videos, lot of Coursera contents you can see. But compared to all the other things, this is where I started learning actually. Okay. Andrew Ng Stanford lectures you can definitely refer. All the value iteration, policy iterations, everything neatly explained. Okay, how this accumulation is happening, all these things in his lectures it will be visible. Actually, that machine learning lecture covers many things. Actually, one of the chapters is reinforcement learning. So actually, they implemented reinforcement learning to fly the small helicopter upside down. Okay, the target state was upside down, so it was able to learn automatically through different iteration. You can search those videos also available in YouTube. And similarly, the Caltech video also, all the linear regressions, everything they cover. Okay, these things you can definitely learn. Of course, the trend is like more towards video lectures, video learning nowadays, right? So these lectures you can find online to learn. Coming to the books, if you're asking, Machine Learning by Tom Mitchell is almost like a local author book, even for any students also used to recommend, you can recommend. Okay, because here also you can see all the learnings, including the reinforcement learning, Q learning, everything is neatly explained with why this discount, why this value update, how to do the policy evaluation, all these things are neatly explained. Of course, compared to machine learning by Tom Mitchell, for reinforcement learning, this Sutton and Bato, even they have some lectures also online. This particular book also available free online. You can find this reinforcement learning and introduction. Okay. They started with lot of examples. You can see there's some kind of grid world examples I showed today. Right? So those things with numerical examples also is available there. Okay, something like how it is updated in some of the steps. All these things you can understand. And the difference between this Monte Carlo and temporal difference. All these things are neatly explained in by Sutton and Bato book. So definitely these things I'll recommend. Right. I think today's session, I think we can wind up with that. Of course, the reinforcement goal, all these things are based on Bellman equation we are working with, basically. Right? It's very classic. Okay, so based on the environment interaction, we are trying to learn something. So definitely the results will be optimal. Okay, so with that, I'll conclude today. Right? If you have any queries related to this, definitely I'm open now.
Participant, unmute yourself and ask if there is any queries. Okay, sir. If there is no queries, we can conclude.
Yes, sir.
So thank you, sir. Thank you very much for your session with examples of bicycle riding and day-to-day activities. And thank you for the online videos and books you suggested. With your words, hope the participants will maximize the learning and get the success. Thank you, sir. Thank you so much.
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir. Thank you very much.
Thank you all. Kindly fill the feedback. Thank you.